Yeah. Okay. Hello, everyone. Welcome to another Learning Glass journey. Today, we'll talk more about combustion and like how to analyze and keep track of these different molecules and species that are being produced and consumed. So, in a typical combustion process, there's a flow in and out of the system. So if this was our combustor here, it can be a variety of shapes and sizes depending on the application. In some cases, you have this fuel and air coming from different streams, or they could be mixed. So here we would have, in this case, let's have methane fuel flowing into this combustor and air flowing into the combustor as well. Then they mix in the chamber and they burn in the chamber. So there's a lot of details that goes on inside here, but from a thermodynamics perspective, most of the time we just ask, okay, what is the final state? What happens for the flow, the properties of the flow coming out of the combustor is what we use in the first law and second law analysis to find out what happened in between, in a sense of this energy heat out, or the extent of reaction and things like that can be analyzed from a thermodynamics perspective from what happens at the end. So in this product stream, we would have this full oxidation to CO2. The fuel gets oxidized, but in some real life, in most real life cases actually, for a few different reasons, you would form carbon monoxide, which is related to CO2. It's just not fully oxidized. So this would be a product of incomplete combustion. This, happens, but we won't go too many details of how that works and the details of that. But it's just a possibility when combustion is not complete, and I'll talk a little bit about that soon. So these are our combustion products, and these are all gases from the hot exhaust. But as we may have seen in our experiences with combustors, if you were to run this through some pipes or just even in the sky, the fact that this is hot, when it comes out of the flame and then it cools down eventually, either at the end of the tailpipe or in the sky, you can have this product stream coming out, but then there's be water condensation. Why? Because water is formed, and if the temperature drops, you reach the dew point. The partial pressure of water vapor in this mixture here reaches its saturation condition due to a lower temperature. So in some cases, or in all cases really, but at the tailpipe you might see it, or on a cold day you would see white fog coming from your tailpipe. That white fog is condensed water droplets that get exposed to the atmosphere, and the temperature is cold enough where the water vapor inside of this exhaust mixture, it reaches its saturation condition. So that's what happens sometimes. So condensation of H2O vapor occurs as the combustion products cool, because of course they're hot at the flame. So this may cause rust. may cause corrosion if the water is not flushed away in the pipes, or if it collects somewhere where mold can develop. You can also, that can be a source of the mold, the water from these combustion products. Another thing, another thing that can affect this, or something else that's related to this condensation process, is that combustion researchers or engine designers, they're interested in how this fuel burns. If they want to analyze, some measurement or analysis of combustion product concentrations is done, like measure. What I mean by analysis is measure the concentrations, is done after mixture is dried. This would be the dry mold basis. So if you were to measure these concentrations, you would condense out all the water on purpose. You would like cool it so that you reach a dew point, and then you drip away all the water, and then you would measure what you have left, because it's easier, because a lot of these instruments, it's easier to measure without water. So that's common in this combustion world, where both for performance and material considerations, it would be interesting to know when this water will condense out. That's something that is in the tailpipe and atmosphere. We may have seen this white exhaust. And also, if we wanted to measure these concentrations, which is important because it's very hard to get to design what's happening in this box, and to predict beforehand what's going to happen. Now it's possible, but the only reason why that's possible is because we have a lot of experience measuring this directly, and that through this experiment, measurement, and modeling iterations over 100 years, we've gotten better at predicting what's going to happen. But before that, we had to rely on measurements. Okay, so for example, for burning methane, CH4, in air, let's say we have an analysis of combustion products on a dry mold basis. So if we have a measurement, analysis is like the measurement of this mixture, but on a dry mold basis. Given that, what can we do? Okay, let's do that. So if we measure on a dry mold basis that this dry mixture has a 9.7% mole of CO2, it has 0.5% bimole of carbon monoxide, which is a sign that this combustion process is not perfect. And we have 2.95% of oxygen, which is a sign that we fed in more oxygen than we needed for the theoretical conversion of fuel to CO2, and the rest is nitrogen. So there's a couple things with this mixture. This whole thing equals 100%. So we took out all the water. This is the dry mold basis. There's no water in this analysis. We took it all out before we measured the rest. And this is a sign of incomplete combustion. So this happens for a few reasons. The main reason is because of bad mixing, which is very hard to do. Even in real engines, it's bad mixing, but it's the best they can do. The reason why we still have carbon monoxide in our atmosphere today, why we have soot particles, black particles coming from our exhaust today, is because as hard as they tried, these engine designers, they still cannot get a perfectly mixed air to fuel mixture in the chamber in the time that they want. So there's a trade-off. They want to burn fast, you want to have a high revolutions per minute, and you want to get this power out, but you don't want to wait for complete mixing. So we haven't been able to perfectly get mixing, and when that happens, there's a possibility of some fuel-rich pockets, like pockets of deficient. So what that means is that because the mixing is bad, what we mean by that is during this cycle in your cylinder, burning the gas or in another combustor, at some spot in the combustor, there was not enough oxygen because it's not mixed right. And because what's related to bad mixing is that there's not enough time to either mix or burn. You didn't give enough time for this to happen in terms of converting this fuel all the way to CO2. Some of it was left as CO. Or you had, in some cases, this is purposefully done, you have excess fuel. These are all related. Sometimes they all happen by accident, sometimes they're on purpose, or not on purpose, but it's just the fact that this combustor, if you have a hypersonic engine in a super fast plane, it's very hard to get enough time in this combustor of your plane to completely convert to CO2. Mixing, it's always hard to get perfect because you're trying to run an engine fast and you need to get the power out, but you try as best you can to mix this spray liquid fuel in many cases. That's another area where it's hard to get a perfect mixture. Okay, and of course, if we have extra CO2, it could be because of bad mixing, but it's also probably because in many of our combustors, we design it with excess air. And one reason why we design it for excess air is to minimize these problems here. If you have a lot of oxygen, then even if you have bad mixing, it's still possible to completely convert, to completely oxidize. And it also reduces the temperature and things like that. But we won't go too much into those details. Okay, so we discussed this mixture. Let's use it now. So we can write down this combustion reaction with unknown atom balances. So we know that we have methane and air to start off with, and we know what the products are on a dry basis. The question is, how does all of that balance out? So let's write the reaction to help us keep track of how to balance everything out and analyze this. So we have an unknown moles of methane that get fed in, plus an unknown concentration or proportion of air, which is related to 1 mole of oxygen and 3.76 moles of nitrogen. So this gives you 4.76 moles of air with this B to help balance things out. Then, one thing that's unique about this particular problem is that they tell us that CO is formed. And then we can apply this known proportions. So for this, we're going to say this is for 100 moles of products, of dry products. That's going to help us easily use what we know. So we know we have this mole fractions of dry products. So that we're going to specify this balance to say that for 100 moles of dry products, this is the balance that would be. And that's another thing that's unusual for this problem, is because usually we set up this problem per 1 mole of fuel is our basis. But now what we constrain it by is this mixture that we do know, and we do not know. We have to find the moles of fuel. It's not 1 anymore, it's an unknown balance. So if we're using this, we can plug in these proportions that are given by the analysis of the concentration measurements. So that would be 9.7 moles of CO2, this half mole of CO, this 2.95 of excess oxygen in the products, and this 86.85 moles of N2 in the products. Plus, don't forget, this is dry mole, but there is water formed. But we do not know how much water is formed because we took it all out. So now this atom balance is going to help us to find out how much water is formed. Because we know, starting from these points, we can apply mass and atom balances to find how much fuel we needed. That fuel we needed is going to tell us how much water we produced. Because by the conservation of mass, conservation of atoms, this all has to balance out. Okay, so let's do that. The atom balances. For C, carbon, it's 9.7 on the products plus 0.5. So there's 1 carbon on the CO2, 1 carbon on the CO, and they're given by this amount on the concentration balance. That has to balance out with this left side of the reaction. Okay? So hydrogen, there's 2 hydrogens in the water, but we don't know how much is produced, so that's some unknown variable. And we know that there's 4 hydrogens on the fuel, but that's some unknown variable. Okay? For oxygen, there is oxygen in a lot of these species. So there's 2 oxygens on CO2, there's 1 on CO, there's 2 on oxygen excess in the products. And then there's this 1 oxygen on the water. So that all has to balance out with this inlet flow of oxygen in the air. Okay, so if we were to solve that system of equations, we would get A is 10.2, which comes out from this first part. B is 23.1. C equals 20.4. So that's these coefficients for the methane at the beginning, the oxygen at the beginning, and the unknown amount of water. So there's 20.4 moles of water per 100 moles of dry products. Okay, so that's good. That's some progress. Okay, so let's measure the, another question is, what is the air to fuel ratio? Okay, let's analyze that. Now we know the moles of air coming in, we know the moles of fuel coming in. The moles of air coming in is related to B, but we have to remember that for every 1 mole of oxygen and 3.76 moles of nitrogen, that's 4.76 moles of air, because we're considering air to be a mixture of those two. So if we just add those proportions together, we'll get 4.76 moles of what? Of air. Okay, so by definition, the air to fuel ratio describes something at the beginning. It's not, the air fuel ratio is what we use to describe the inlet condition in the combustor. And we use the products to trace back what happens at the beginning. So by definition, that's the mass of air divided by the mass of fuel. You can also define this in terms of moles. That would be this hat on top of it, but most of the time when people talk about air to fuel ratio, it's in terms of mass. So we can find that from the moles of air and use the molar mass, the molecular weight, to convert to mass. So we know a lot of this, so we can say that this equals B, the proportion of in front of this air, but we have to remember that this is because it's B plus 1 mole of oxygen and 3.76 moles of nitrogen. That's where this 4.76 comes from. And then we can use a molecular weight of air, which is about 29 kilograms per kilomole. And then C is the proportion from the methane, and the molar mass is about 16. So that is 19.5 kilograms of air per kilogram of CH4. That's the air to fuel ratio. Okay. So that's what we did. We said we know we have an analysis of the products. It's normally analyzed and measured with the water condensed out, and we can apply that to the known combustion reaction with the stipulation that we have some completely incomplete oxidation of CO, of carbon, which makes CO. Then we have to remember that there is water formed. We have to use these atom balances to find out what the proportion of water that is formed. By doing that, we can find the air to fuel ratio that we started out with. Okay. So another question is, how much, if we have oxygen left over, that probably means that we had, if it's a large amount, then that means that we had excess air fed in. If it's a small trace amount, that might mean that the mixing was not good enough, that there was not a huge excess. It was just that there was not enough mixing to get the oxygen to do its job. But this is, let's see what these atom balances say to find out if how much the excess air there would be. So to do that, to find the excess amount of air, we have to find the theoretical amount of air. We have to find that, which is the stoichiometric amount, meaning what is, for a given 1 mole of methane, how many moles of oxygen do we need to consume that methane without having any excess? So it's what is the perfect balance between methane and oxygen? So to do that, you need to balance out the atoms for an ideal theoretical complete combustion of methane. So complete means you only form CO2. That's the normal basis of our theoretical excess versus theoretical stoichiometric. So that's what theoretical means. It's balanced. There's no excess at the end. Complete means you only form CO2. Ideal, that's all these is what we're different ways of saying that. So what that would happen would be per 1 molecule of CH4 in air, you need 2 molecules of oxygen, but that would be tied to the air, so you need this proportion. So this would be 2 times 4.76 moles of air, or 2 moles of oxygen, to form 1 CO2 plus 2 waters plus the nitrogen. So that would be the ideal complete theoretical combustion. So the air to fuel ratio in that case would be the stoichiometric or the theoretical would be, you have 2 moles of air times 4.76, so it's this 2 coefficient times 4.76 because you have both air and nitrogen in there. Then the molecular weight of air, then the 1 mole of methane times the molecular weight of methane. So that should give you 17.3. kilograms of air per kilograms of methane, stoichiometric. Okay. So we can use that over here. So the percent excess equals the A to F that you actually have. It's related, so we know how much theoretically what the proportion would be. So we know what we actually have. If we compare that to the stoichiometric, that will tell us whether we're above or below what we need. Then subtract that by 100%. So we know how much we have, compare that to how much we need, and then convert that to a percent. That'll give you the -1. So if we don't subtract this 1, that will give you the theoretical percentage relative to theoretical. But we can trim off that 100% and say how much excess we have. So this would be 13% excess air. Because we know what the theoretical balance would be if you don't have any extra oxygen. Okay? So what about the water? So this products were on a dry mole basis. The water condensed out. So how did the water condense out? Well, we know how to figure that out because we know about psychrometry and saturation pressures and steam tables and such. vapor domes. So water? What about the water? Okay, so we know that C is the coefficient for water. It's 20.4. So for 100 moles of fuel, this dry products, 100 moles of dry basis, then the mole fraction of water is related to these 20.4 coefficient, this 100 of everything else, plus the water in the products. So that means in the products, you have 0.17 mole fraction of water. Okay, if we assume that it's vapor, then we can find the partial pressure. So the partial pressure of water, which we also call partial pressure of the vapor in the psychrometry chapter, equals the mole fraction times the total pressure. So at 1 atm, the partial pressure of the vapor is 0.17 atm. Okay, so if we look at the steam tables, the dew point is about 57 Celsius. So for this partial pressure, so P sat equals 0.17 atm at 57 degrees Celsius. That's why all of this is related. It's saying that if we know the mole fraction of water in the products, and if it's at a certain pressure in the surroundings of the gas phase, 1 atm is a good reference point in most, in San Diego at least. That means that the partial pressure of water vapor in the exhaust when it's hot is 0.17 atm. If you keep that constant mass loading, that constant pressure of the mixture and of the partial pressure of vapor, if it cools down to 57 Celsius, that partial pressure that you have approaches the saturation pressure at 57 Celsius. So at a hotter temperature, the saturation pressure is higher, meaning that your relative humidity is less than 100%. But if you approach 57 Celsius, the relative humidity becomes 100% because your actual partial pressure matches the saturation pressure. That is the dew point. That is relative humidity to 100%. That means you have condensation. So that's the one benchmark temperature for this case, is that at 57 Celsius, the water will start to condense. Okay, so that's some things to how all of these are related in terms of analyzing this combustion. We started by saying that we had a measurement of the concentration of these products on the dry mole basis, which means that we condensed out all the water, then we analyzed what's left over. That gave us a basis to analyze what happened before and after. So on this dry mole basis, we have mole fractions. We can say, okay, for 100 moles of these dry products, this will be our starting point to do these atom balances. And from the atom balance, we got the air to fuel ratio we started off with, and we got the amount of water we formed. And we can ask the question of, for this given amount of water we formed, what is the partial pressure and what is the point at which it will condense? Okay, so that is summarizes one aspect of this combustion. I'll see you guys next time. Thank you.